another speaker, the last speaker of this session, which is Yelyzaveta Pulnova, and she will speak about particle acceleration in the hotspot of some radiogalaxy. So go ahead and good luck.
Right, thank you.
Just share your screen, please, before you
I hope
start.
you hear me well. Thank you very much.
You are welcome.
Okay, can you hear me?
Yes, we can hear you.
Okay.
Just there are some probably.
So good afternoon. Could you repeat, please?
Maybe it would be better if you stop your video because it's.
Okay, I see.
Thank you.
Okay, let's try it. Let's try it like this. Today I will present some results which we get with my supervisor. We are studying the particle acceleration in the hotspot of the galaxy on the example of the radiogalaxy 3C105. We are interested in so-called ultra-high energy cosmic rays, which were mentioned today. I will just introduce them in more detail. So these are rays which energy exceeds the 10 to the 18 electron volts. You can see on this graph the dependence of the flux on the energy in the logarithmic scale, and this distribution of on this distribution we see the contribution of the different sources for these particles. There are more local ones, the solar origin, and then it follows with the galactic and extragalactic ones. And the physical mechanism of the acceleration of these ultra-high energy cosmic rays are still the open question, and we present our work to contribute to this topic of possible sources of this ultra-high energy cosmic rays. So let's have a look at the possibilities, possible origins of these rays. It is possible to calculate the upper limit for the energy of the particles. And now the idea of this calculation is very simple. We want this particle to be a part of some system where it accelerates. So if the Larmor radius of this particle becomes greater than the size of this object, then particle escapes and cannot be accelerated further. That gives us this upper limit for the Larmor radius, and then with this we can calculate the upper limit for the achievable energy. And if we consider energy as the parameter, we see the dependence of the object size on the magnetic field. It is the inversely proportional, and can be visualized on the so-called Hillas plot here. Yes, so one more time, we have on the axis the magnetic field and the size of the object, and the diagonal line is given for the some given value of the energy. Here, for example, we have 10 to the 20 electron volts, and sources which lies on the particular line can have the potential to accelerate particles to the given energy. You can see that there are a lot of sources from neutron stars up to the galactic clusters, but today we will talk about this radiogalaxy jets. Okay, just a few words about the radiogalaxies. The radiogalaxies are the subset of active galaxies nuclei, and these are the radio loud galaxies, so we can see the nice images in the radio range. And typical structure on the example of Cygnus A is here. So we see this active galaxy nuclei and produced jets, both sides, lobes. And for us, we are the most interesting area is this hotspot. And let's have a closer look to its structure. When plasma from the jet meets the external medium, it creates so-called the bow shock. This is the first one, the first shock that we see in this picture, but there is actually one more, which we call the reverse shock, and we called it we called it like this because of it's originating from the collision of the jet plasma and the reverse backflow of this plasma. And in this work, when I will mention the acceleration of the shock, I will mean the acceleration of this reverse shock. And we use our source, we calculate things on the example of the radio source 3C105 South. This is the image which were taken on the frequency 8.4 gigahertz. And at this frequency, the source have three nicely resolved knots, which are denoted as S1, S2, and S3. So let's have a look at the model. We use the diffusive shock acceleration model. And the idea of this acceleration mode is as follows, that particle can gain the energy after crossing multiple times the shock front. For this mechanism to work, we need some scattering centers in the plasma, and in the large majority of the cases, these scattering centers are magnetohydrodynamic waves, which naturally arise in the plasma while particles with high energy propagates through this medium. Just one note about this, the notation. I will mention the upstream and downstream. When I talk about the upstream region, I mean the region just in front of the shock, and the downstream is the region right behind it. Why we are concentrating on the diffusive shock acceleration? Because its theoretical prediction is in a good accordance with this with the spectrum which we measure on Earth. The consequence of this theory is the power law distribution of the non-thermal particles, and we measure the thermal particles. Yes, so we proceed to the calculation. The aim of this work is to calculate the maximum energy of the cosmic rays. In our case, these are protons, but let us talk about the electron first. Here you can see the spectrum, synchrotron spectrum of the one electron. And when we are talking about the physical object, let's say active galaxy nuclei or anything else, just plasma, we have a lot of electrons, which every of each emits this spectrum. So when we sum this contribution, we see that it produces the power law distribution for these photons of synchrotron emission. And this line we can measure, and according to our observation, it has some maximum value. So there is the maximum frequency, which we call the cutoff frequency, which is the maximum frequency for this source that can exist. And using this equation for the characteristic energy of the particle, we can just put here this maximum frequency and calculate the maximum energy. And that's what we did. The result for the electron for a given hotspot is here. They are of the order of tera-electron volts. But now let me introduce to the estimation of this magnetic field that is required for calculation of this. Because it could be more trickier than this just measuring. We should estimate this. So what we did, we assumed the special configuration, which is called the equipartition magnetic field. When we given that one plot the energy density as a function of the magnetic field, we see that the field magnetic energy behaves like this, and the particle energies behave like this. And there is a special point, the intersection of these two curves, which means that there is the equal distribution, equal portion of energy is distributed in the field and in the particle. And you can also mention that this magnetic field value is very close to this energy density minimum value, magnetic field of this minimum energy density value. And that's why we use this, because it is close to this reasonable value for the energy density. Just with more math, it is the same thing is presented on this slide. So we put into equality this magnetic field and the particle energy density. And from this, we do it separately for electrons. We get from this the magnetic field, the equipartition magnetic field for the electrons. And then by rescaling this energy density, we get the expression for the equipartition of protons and electrons together. And these values are here. And just to emphasize that these values we used for calculating the maximum energy for the electrons, which I presented on the previous slides. Well, and our next aim will be the discussion of the physics behind this limit on the electron maximum energy. So the common assumption is that this energy is restricted by the synchrotron cooling. So the leptons are moving in the magnetic field and then radiate. That's why their energy decreases, and it has some consequence to this maximum value. And mathematically, we can express this in terms of this acceleration time and cooling time. And the idea is that when the cooling time is greater, then we can access some energy, and otherwise it will cool quickly then accelerate. So for the maximum energy, we should assume the equality of these times. But these actually lead to the unreasonable consequences. We get unreasonably large jet plasma density and diffusion coefficient, which were calculated in this reference. So instead of this, we propose another mechanism which could work. And for this, we need the amplification of the magnetic field and the turbulence in the downstream region. Why we need this? Well, we just measure the synchrotron emission, and there is the minimum, the requirement for a minimum magnetic field that should be present in the system to obtain this result. So it is just given by the observation. And the second one, we want particle to be in the close region behind or near the shock for a long time to let it cross back and forth multiple times. Otherwise, if we don't have in the downstream region any turbulence, particle will just become magnetized and follow the magnetic field line and escape the system. So we don't want this. That's why we assume this turbulences in the downstream to let particle go back to the upstream. And it was shown that this is possible if we consider the non-resonant hybrid instability. So both these requirements can be fulfilled. So what this mean for us if we want to estimate the energy of the news, because we don't have to calculate anything else. It is given by the fact that the magnetization mechanism is the same for electrons and protons, and that means that that this maximum energy will be the same. And I repeat, this is of the order of tera-electron-volt, which is not unfortunately high enough to explain the ultra-high energy cosmic rays. Well, and to summarize what I've just presented, we discovered that the maximum electron energy cannot be determined by the synchrotron cooling. Instead, we propose that it is determined by the determined in terms of magnetic field amplification and magnetization of the particle in the downstream. For this purpose, we've assumed the non-resonant hybrid instabilities, which are also called Bell instabilities, and the perpendicular configuration of the shock. And as a result, we got values which are low for saying that this source can accelerate particles to these ultra high energies.
So thank you, Yelyzaveta, for your nice presentation. And are there any questions or comments? Probably not. So
I would ask, if I may.
Yes.
Can you say anything about effects of anisotropy of this maximum energy? I mean, is it isotropic with respect to the view direction from the observer on the object?
Well, it was not the scope of this work, but from what I know, it is there is anisotropy in this distribution, but I'm afraid I cannot tell a lot more about this.
Okay, I was wondering whether one could see different values of this maximum energy from different directions.
Probably not. But I have no calculation to well.
Okay,
to
we
present,
can talk later.
Yeah.
Yeah. Thank you.
So thank you. And
so can I ask a small question concerning magnetic field? So I didn't, or maybe I missed. What is the strength of equipartition magnetic field that you estimated for this source?
Yes, I will show it to you. It is no, it's 1 second. Yes, these are here. So we got hundreds of microgausses.
Okay. But you also assume that it is amplified, right?
Yes. But
how?
I didn't. Yeah. For now, the work is in progress, and we are now not. I don't have the results for the values of this amplified magnetic field at this point.
Yes, but do you think that it can be increased to one order of magnitude or 2 orders, or I don't know, a few times? Just to have some idea.
Yeah, I think that it. As I said, I didn't calculate it yet, but it could. I think it could be 2 orders of magnitude, or like this, something like this.
Oh, thank you very much.
You're welcome.